So before I kick things off, there's a couple of EHEC relevant announcements. The call for papers for fall EHEC seminars is out. It's on the website. So if you submit to that by August 15th, which is the due date, that'll put you in the running for giving an EHEC seminar somewhere between October and December, coming up here in the fall. Also, for next year's EHEC lineup, there are 2 invited talks already. That's David Cutler and Sarah Miller. And the dates, I think, are TBD on both those speakers, but I feel like there's no uncertainty around the fact that they will give like really interesting and good talks. And then lastly, relevant to today, right after this talk is over, kind of hard at 2:45 Central, there is an AshEcon hangout in Kumo space. And so there should be a link in the chat or a link in the email announcement about it. And so you should be able to move over right there and interact some more. So I am going to get us started off. I'm really excited to hear Jonathan Roth talk about all his work and all related work on diff and diff. I think my new sort of line about what has been happening in this area is that everybody out there is kind of a Bayesian with a 2-way fixed effects prior. Okay, so like that's what we knew, but there's a lot of new information about how we can and should be doing our diff and diffs, and the more confusing it is, the less we update. And so it's really nice to have econometricians like John walk you through a lot of what's been going on. So for that, for example, you can see his recent review article with Pedro Santana and John Poe and Alyssa Belinsky on a huge range of issues. But I think even more than that, I think John comes along and answers these really hard questions that I think we could maybe sort of have thought a little bit about, but probably not answered. John can answer them. So he can tell you a lot about inference and how to do more complicated or more appropriate sorts of inference in these settings. He can tell you about what you should do if you don't think your design is like impeccable and perfect, which probably we should all be thinking about a little more. And so instead of kind of waving hands, I think John can pin down a lot of answers there. And so I'm going to hand it over to him to get going on some of this, but this is all going to be topics that I think are worth thinking about and probably incorporating into the kind of applied papers we write using diff and diff analyses.
All right, well, thanks so much, Bacon, for the overly kind introduction. The talk I'm going to give today is titled Difference in Differences When Parallel Trends Might Be Violated. This is going to pool across a couple of different papers of mine, as well as I'll talk a little bit about some work by other people. To kind of set up what I'm going to talk about today, it's well known that the validity of the difference in differences design relies on the so-called parallel trends assumption, which intuitively says that if the treatment of interest hadn't occurred, our treated and our control groups would have had outcomes that evolve in parallel on average. In practice, we're often unsure about the validity of this assumption ex ante, meaning before we look at the data. And so why is that the case? Well, often when we're using difference in differences, we know that the treatment of interest wasn't really randomly assigned. And so there may be some confounding factors that influence whether some group is likely to get treated or not. And so we might be worried that those things that influence whether you get the treatment or not are also correlated with some time varying confounding factors. So for example, if we look at states that raised the minimum wage versus states that didn't raise the minimum wage in a particular year, it might be that states tend to raise the minimum wage when the economy is booming and employment is growing really fast, so that if they hadn't raised the minimum wage, the employment might have increased more in, say, the states that raised the minimum wage than the states that didn't raise the minimum wage. So maybe worried about these time varying confounds. And then these issues are kind of compounded by the fact that parallel trends can often be sensitive to the choice of functional form. So even if I had parallel trends for, say, wages, I may not have parallel trends for log wages or vice versa. And so there's often a lot of uncertainty, even if I don't think that the confounds are sort of time varying, whether they sort of affect the outcome in an additive way in levels versus in logs versus in some other transformation. And so before we look at our data, we're often a little bit unsure about the validity of the parallel trends assumption. But I think one of the really nice things about the diff and diff design which if I had to speculate is one of the key reasons that it's so popular in empirical work, is that it has this really nice built-in plausibility test. So we usually don't just have panel data on 2 periods. We usually have a bunch of periods before the treatment occurs. And so we can test for pretrends, right? So we can say, were the groups moving in parallel prior to the treatment? If it looks like they were moving in parallel prior to the treatment, then it seems somewhat plausible that without this treatment occurring, they would have continued to move in parallel. If they weren't moving in parallel prior, then we're sort of skeptical of this assumption, and then we're going to have to consider some other design. I don't want you to take away from this talk that testing for pretrends is not a good thing or a natural thing to do. I think it is a very natural way to assess the plausibility of the parallel trends assumption, but it's also not perfect. So it's not always going to tell us, do we have a good design or not? And so there's been a recent body of research, including several of my own papers, about some of the limitations about testing for pretrends as a way of sort of preventing us from using difference in differences designs when parallel trends is violated. And so today's talk is basically going to have 2 parts. The first part of the talk is going to be about, well, what are the limitations of pretrends testing? And then the second half of the talk is going to be, well, what can we do about it to make our difference in differences analyses as credible as possible? All right, so in the talk today, I'm mainly going to focus on 2 of my own papers. My forthcoming AR Insights paper titled Pretest with Caution, Event Study Estimates After Testing for Parallel Trends. And then my paper with Ashish Ramachan, which is titled A More Credible Approach to Parallel Trends. It used to be an honest approach to parallel trends. So thanks to our referees for suggesting an improved title. And so I'm going to mainly kind of focus on my own work, I guess somewhat selfishly also because that's what I know the best. But I don't want you to think that I'm the only one working on this topic, and there are a lot of other really interesting papers in this space. So I have a few citations on this slide here. And if you want to know kind of all about work on this topic, in the review paper with Pedro Santana, Alyssa Belinsky, and John Poe, which Bacon mentioned, we have a whole section on kind of what to do if you're worried about violations in parallel trends, both how can you sort of include covariates, and then also how can you think about violations of parallel trends, even conditional on whatever covariates you included. So if you're kind of interested in what I talked about today, there's sort of a lot of other stuff in this space that I invite you to check out that section of our review paper to explore more. All right, but so then kind of I dive into the material of sort of starting out with what are the limitations of pretrends testing as a way of sort of detecting when the parallel trends assumption is likely not to hold. And so I'm going to walk through 3 different issues with sort of conventional tests for parallel pretrends. And so the first issue I want to talk about is that pretrends tests may have low power, meaning that because of noise in the data, even if parallel trends is violated, we may not detect a statistically significant pretrend. And so I think this is a very widespread problem, and I'll show you some more systematic evidence, or at least refer to some more systematic evidence later in the talk. But I think for illustration, it's useful to start with one example, which I think is sort of representative of this literature. So I hope you won't come away with the impression that I'm sort of just trying to pick on this one paper, but I think kind of it's useful to illustrate with a single example kind of a broader problem in this literature. So I want to start with this example from Qi and Wang 2017, where they're studying the impacts of placing college graduates as village officials in China. And so they use an event study approach where they're effectively going to compare the trends of treated and untreated villages before and after the introduction of this treatment. And so this was before the sort of 2-way fixed effects revolution that people like Bacon and others had kind of focused on, where 2-way fixed effects may not give you sort of what you think it's giving you. Here it's actually basically okay because this treatment is essentially non-staggered. There's like very slight variation in treatment timing, but that doesn't really seem to make a difference. So you can do the same thing sort of if you just use all of the units that were treated at the main time. And so they're going to run this regression where they regress the outcome on indicators for time relative to treatment and unit and time fixed effects. And so they're plotting here. Can people see my cursor? Can you see, Bacon, can you see my cursor? Yeah, okay, good. So they're plotting here sort of these estimated coefficients. So the -1, the period before treatment, is normalized to 0. And then basically each of these 3 coefficients to the left are showing the differences or estimated differences in trends between these 2 groups prior to the date of treatment. And then these 4 coefficients to the right are showing the estimated treatment effects, say in the immediate year, the 0th year of the treatment, the 1st year, and the 2nd year, and the 3rd year. And so one of the reasons I chose this paper as an example is it has this nice quote that I think sort of nicely summarizes what people are doing in this literature under the status quo. So they write that the estimated coefficients on the leads of treatment, meaning these 3 pre-treatment coefficients, are statistically indistinguishable from 0. And we therefore conclude that the pre-treatment trends in the outcome in both groups of villages are similar. And so villages without the treatment can serve as a suitable control group for villages with the treatment in the treatment period. So basically what they're saying is, we're going to test, we can't reject the null that these 3 pre-treatment coefficients are 0, they're not significant. So it's compatible with the null hypothesis that parallel trends holds in the pre-treatment period. And so we're going to interpret these 4 post-treatment coefficients as if they're unbiased estimates of the treatment effects of interest. And so if I could put a little bit more statistical structure on what he and Wang are saying and what's common to do in this literature, they're basically saying we're going to test the null hypothesis that these 3 estimated pre-treatment differences in trends are in the population actually all equal to 0, so that the true coefficients that are estimated here are actually equal to these 3 green dots that I've drawn in the plot. And indeed, if I run an F-test for that joint hypothesis that these 3 coefficients are actually equal to 0, these green dots, I get a p-value of 0.81. So by conventional metrics, I can't reject the null hypothesis that these groups were moving exactly in parallel in the population in the pre-treatment period. And if they were, that would be a pretty good sign that they'd be likely to move in parallel in the post-treatment period if this treatment hadn't occurred. But the reason that that's perhaps not the most satisfying argument is that I can also draw these 3 red dots. And these 3 red dots are drawn, are sort of cooked up in this study, in this example, such that if I test the null hypothesis, that these 3 estimated coefficients are actually equal to these 3 red dots in the population, then I would also get a p-value of 0.81. So I can't reject the null hypothesis that these 3 estimated pre-treatment coefficients are actually these red dots where we have this increasing pre-trend. And that's a bit concerning because if I draw a straight line through these red dots, these 3 hypothesized pre-treatment differences, if I extrapolate that trend linearly to the post-treatment period, I would see that what we'd expect if we continued this difference in trends would lead us to get coefficients of approximately what we got in our estimates for the post-treatment period. If there were actually no true treatment effect in the post-treatment period, we were just sort of continuing this pre-existing linear trend. And then to sort of highlight the point a little bit more, I can also draw these 3 blue dots here. Again, everything in this example is rigged up. So if I test the hypothesis that these estimated coefficients in the population are actually equal to these blue dots, I get a p-value of 0.81. So again, I can't reject the null hypothesis that the true difference in trends is actually these blue dots in the population. But these blue dots are drawn on a smooth quadratic curve. So if I extrapolated that quadratic curve to the post-treatment period, I would think that I would have a bias that's negative. So it's the opposite sign of my estimated coefficients, but is of an approximately similar magnitude. So if this were the true difference in trends, then these estimated coefficients would be about half as large as they actually should be. So what I want you to take away from this exercise is it's true, we can't reject that there was a 0 pre-trend. We can't reject that prior to the treatment, these 2 groups were moving exactly in parallel, but we also can't reject non-zero pre-trends that if we did some reasonable extrapolation of those pre-trends to the post-treatment period, we would think that there would be a reasonably large bias that would meaningfully change our understanding of the magnitude of the treatment effect in this context. And so that's, of course, just one example. But it turns out that actually this is not a problem that's specific to He and Wang, but is actually a sort of fairly common problem. So in my forthcoming AR Insights paper, I sort of did a systematic review of papers published in the AER and AHA journals over the span of about 5 years, and sort of based on simulations doing similar exercises as what I just showed you, it turns out that similar issues exist in a lot of papers. So in particular, in that paper, we evaluate, well, how big would a linear trend have to be such that we would detect it, say, 50 or 80% of the time? And it turns out that in a lot of cases, the bias from such a trend would be of a magnitude similar to the estimated treatment effect in these studies. So this is sort of a widespread problem, not just an issue with He and Wang. Bacon, you look like you maybe had a question there.
I remember reading this sentence and trying to make sure that I understood what it meant. So you're saying that even with 50% power, which is not that powerful, there's often the possibility of like bias that would totally kill treatment effects in these kind of big deal papers. Is that fair?
That's exactly right. So if you think of the slope that we would detect 50% of the time, given the precision of the confidence intervals in the pre-period, which is sort of like marginal power, we'd only detect it half the time. If you think about what would be the bias from extrapolating that slope in something like roughly half of papers, that bias is about as big as the estimated treatment effect. So if it were just on that linear trend, you could sort of just explain the magnitude of the estimated treatment effect with sort of a bias from a straight line and no true treatment effect.
So one other question here. I know a lot of so the power here is based on the precision of the actually reported pre-coefficients, right?
So that's actually not quite true. So there's a distinction that I was trying not to get into, but maybe I should get into here, which is, do you want X anti-power or X post-power? So X post-power looks at the actual coefficients you've estimated and says, what can you roll out? And then X anti-power only looks at how precise they are and say, if this were the truth, how likely would we be to detect it, but isn't actually looking at those coefficients. And so what I showed you earlier with that diagram is the statement about X post-power. It turns out for certain econometric reasons that I think I'd prefer not to get too sidetracked with, in terms of evaluating like what's the average bias in published work, you want to kind of think about X anti-power, like sort of how you do power calculations before you run a study. And so kind of the summary statistics I have here are based on sort of X post power, where the plot I showed you was, the summary stats here are based on X anti-power, whereas the things I showed you were kind of X post power. Turns out X post power in this survey of studies is also not great, but at least the statement I have here is about X post power, X anti-power rather than X post power.
Part of the reason I was asking is that this seems like a place where the kind of inference that you do or things that researchers can do to make their estimates more precise would really matter for how much they feel their estimates are subject to this kind of thing. A lot of the new diff and diff stuff has been focused on point estimates, but this seems like a place where inference methods and precision really can start to matter a lot.
Yeah, so I mean, I think a common theme that you'll see throughout the talk today is you want to think about a lot about not just what are the point estimates for the pre-trends, but also what are the confidence intervals about those. Great, thanks. Great. So that was the first issue I wanted to talk about with pre-trends testing. The second issue, which is a bit more subtle, relates to what are called distortions from pre-testing. And so kind of as an intuitive overview, if parallel trends is violated because we don't have perfect power, sometimes based on noise in our data, we're going to fail to find a significant pre-trend. And so if we only analyze our data as a diff and diff or using a particular specification when we don't find a significant pre-trend, we're analyzing a selected sample from this data generating process. And so when you're sort of analyzing a selected sample, we know that there can be some type of sample selection bias, which in this case is known as pretest bias. And it turns out that in the context of difference in differences, under certain seemingly reasonable data generating processes, it turns out that analyzing this selected sample can actually exacerbate issues related to the fact that parallel trends was actually violated. And so I'd like to kind of illustrate these issues in a sort of very toy simulation that I think will get at kind of the core ideas. So in this toy simulation, I'm going to think about a 3-period model where there are 2 periods, -1 and 0, where the treatment hasn't occurred. And then there's a last period, period 1, where the treatment has happened. For simplicity, I'm going to have there's no actual causal effects in this simulation design. But in the population, the untreated potential outcomes for the treatment group is going to be on a linear trend relative to the control group. So in particular here, the control group is going to have a mean of 0 in every period. The treatment group is going to be on an increasing trend with the slope of delta. In the simulations that I show you, delta is actually going to be equal to 3. And so then we're not going to observe the true population means. We're just going to observe the population means plus some noise, which, to make things super simple, are just going to be IID normal errors in each period. So the nice thing about this simulation design is it makes it really easy to show things graphically. So here what I'm going to do is I'm going to show you a plot. On the x-axis is the 3 periods that we have, period -1, period 0, and period 1. On the y-axis is going to be the difference in the mean of the outcome between the treated group and the control group. So if I didn't have any sampling uncertainty, I saw data for the infinite population. In period -1, the difference between the treatment group mean and the control group mean would be -3. At period 0 would be 0, and at period 1 it would be 3. So basically, the treatment group's outcome is just growing on this linear black line relative to the control group. And recall, there's no treatment effect here, so this is what would happen both in the counterfactual without treatment and if there is treatment. Of course, in any actual data set, we don't see this black line because we estimate things with noise, right? And so actually what we're going to get is something that looks like one of these gray lines, where we get one of these gray dots as an estimate of the difference between the 2 groups in period -1. We get a dot here for the difference at period 0, and then we get a dot here for the difference at period 1. So here I've drawn something like 1,000 simulations from this data generating process. Each of those is a gray line. And of course, just because our data is noisy, even though there's this true upward sloping linear trends, in practice, in some cases, we're not going to find a significant pre-trend. So we're not going to find a significant difference in differences between period -1 and period 0. And so I've highlighted these cases where we don't find a significant pre-trend in blue. And so mechanically, what it means, if we don't find a large pre-trend, it means that the slope of this line between period -1 and period 0 is pretty flat, because the difference of differences between period 0 and period -1 precisely corresponds with the slope of this line, right? The change in the difference at period -1 relative to the difference between the 2 groups at period 0. And so you can think, well, how do we get a flat line in our sample, even though the true line, the black line in the population, is increasing? Well, we tend to get a flat line if we get noise at period 0 that makes us underestimate the difference between the treatment and the control groups. So you can see that these blue dots at 0, these estimates of the difference between the 2 groups at period 0, where we don't find a significant pre-trend, tend to be below the true difference, this black square here at 0, right? So these estimated differences when we don't find a significant pre-trend tend to be negative. But then because of a mean reversion type of effect, since we're starting too low at period 0, the slope between period 0 and period 1, which corresponds with our post-treatment difference in differences estimate, tends to be very steep, right? So this is easiest to see, I think, if I show you an average over, here I have an average over 1 million draws. So if I averaged over 1 million draws and I looked at the cases, I looked at all the cases, I would just on average get this straight line, this black line, where I don't really see much break between the pre-treatment period and the post-treatment period. But if I look at the cases where I don't find a significant pre-trend, then on average, the pre-trend is not 0, but it's relatively flat. It has a slope of only 1.4 compared with the slope of 3 in the population. And then if I look at the post-treatment, in population, on average, it's 3, but in the cases where I don't find a significant pre-trend, it's 3.8. So even though on average, these groups, they're just the treatment group is growing linearly relative to the control group in all periods. When I look at the cases where I don't find a significant pre-trend, it actually looks like there's an effect here, right? It's fairly flat in the pre-treatment period, and then there's an even larger sort of estimate in the post-treatment period. So in the cases where I don't find a significant pre-trend, it looks like something is actually changing at period 0. Bacon, did you have a question there? Are there any questions?
Yeah, so
I'm happy to stop here.
Okay, so one thing I've wondered about this point is that this feels kind of like a publication bias type of thing, like it applies to a whole literature.
Sure.
And how should I, as like one person running diff and diffs, choose what to do when I have an idea, get some data, run a diff and diff, and there is either a great looking flat pre-trend or a bad one? I mean, how should I tell if I'm doing something that's causing this kind of bias versus just picking a good or a bad design?
Yeah, so I think that's a great point. Let me try and attack it from a couple of different angles. So the first angle is, I think, this point, and this is articulated in the pre-testing paper a little bit better than in the slides here. But I guess they're kind of trade-offs. If you think about, should I require you, or should I choose the design? Say, actually, to make it simplest, say I have 2 designs. One of them, the pre-trends look very flat, at least based on the point estimates, and one of them, they look not so flat. But say the confidence bands around those pre-trends are pretty wide, right? So it could be, if I take the one that it looks better, that I'm actually choosing one where the true difference in trends in the pre-treatment period is smaller, so I'm getting what we think is the better design. On the other hand, it could be that if those confidence intervals are really wide, it could be that in truth, they have the same pre-treatment difference in trends, but now I'm selecting one where I had more noise in the pre-treatment period. And based on this type of logic in the simulation that I just showed you, that would actually mean that you're selecting the one where on average we have worse bias when we actually estimate it. And so I think the key point here is not that like pre-testing always makes things worse, but the point is that if the pre-treatment estimates are very noisy, it's not obvious whether we're selecting a design where the truth is actually very good, or where we're selecting a design where we just had a lot of noise in the pre-treatment period. And so the data can't really tell us which of those situations we're in, because by definition, the data is noisy. And so I think one of the takeaways from this is, we're economists, we often know a lot about the situations that we're studying. And this seems like a situation where we want to bring in economic knowledge. So if you told me it's basically randomly assigned, based on institutional knowledge, whether you're in the treatment group or in the control group, if I look at your pre-trends and they're really noisy, but I can't reject 0, that seems not so bad, because I was pretty confident ex ante that the truth is that, these groups are pretty similar. On the other hand, you tell me that these groups are wildly different on all covariates. They have very different baseline outcomes, but I can't reject that they're, moving in parallel, but my confidence intervals are really imprecise. Well, that's the case where actually the data is not telling me that much about the pre-treatment differences and trends, and I didn't have that much confidence ex ante in the design. So that's, I think, the case where you want to be a little bit more skeptical.
Okay. This brings up
help?
Yes, this brings up 2 follow-up questions. So I don't think I appreciated the link between the points you make about pretest bias and then the points you make about how to address low power in the pre-trends test. So is it true that this pretest bias would be not so bad if people chose some of the better pre-testing methods I think you're probably about to discuss? And then that's point 1. It's like, maybe you could elaborate on the relationship between the pretest bias and the pre-testing methods. And then the second, James Donahoe asks in the chat a good question, kind of related to what you just brought up, which is how does this kind of pretest bias relate to methods that are trying to match on observables or control for observables? And I don't know if you're going to talk more about the role of covariates in diff and diffs. That's probably a whole EHEC of its own. But if you could say anything about how this interacts with control strategies, which is often the step 1 for us regression runners on what are you supposed to do when this looks bad? Well, maybe it's good for some subgroup or some matched groups.
Yeah, good, all great questions. So I guess the first thing is kind of if you have a high-powered pretest, then in most cases you'll sort of reject if the design is bad. And so it's not necessarily the case that the bias is going to be small when you fail to reject, but you sort of if you thought about a world where, half of the research designs had zero pretrends, it was basically randomized, and then half of the designs had some bias. So if the pretest is really powerful, then most of the cases where you analyze, the data are going to be cases where pretrends are actually zero. And so the bias will be relatively small. The bias in the cases where you mess up may be pretty large, but you kind of care about the product of what's the probability that you mess up and don't detect the design times the expected bias conditional on messing up. And so if you're really well powered, then at least that first term, what's the probability that you mess up, will be small. You don't necessarily have a guarantee that the bias conditional on messing up will be small, but hopefully that product at least will be small. If sort of the probability you mess up is relatively large and the bias conditional on messing up is large, then you sort of have the product of two relatively large things. And that's where we kind of run into the biggest problems. I guess what I'll show you later when I get into the honest DID stuff, it's going to have this nice feature where your confidence intervals will get bigger. Your confidence intervals for the treatment effect will get bigger, kind of the wider are your estimates of the pretrends. So your sort of confidence intervals are going to take into account the fact that we have uncertainty over what the pretrend is. And that's kind of the opposite of what sort of the standard pretesting regime suggests, which is that if I have the same point estimates, kind of the confidence intervals are really wide, they're not significant, and I say, oh, I can't reject, zero pretrend. Whereas if I had, say, a really small pretreatment coefficient, but I had tiny standard errors, I may actually reject. And so in some sense, like in the status quo, kind of to pass the test of is my design good, I want my standard errors in the pre-period to be big. And I think when you think about that hard, that's actually not what you want to do. And so one way that the honest DID approach, which we'll show you later, kind of addresses this, is going to take into account the confidence intervals in the pre-treatment period. And so if those are really precise, even if they're significant, but if the magnitudes are small, you'll tend to get a tight confidence interval for the treatment effect. If they're close to zero, but the magnitude, the confidence intervals are massive, then you're going to have, a larger confidence interval. So I hope that clarifies. Oh, I think that clarifies your first question. Your second question, or the question from the chat, which was a great question, was about kind of what happens if you say like match on pre-treatments, say outcomes or something. So either match diff and diff if you're conditioning on some covariates that are highly correlated with lagged outcomes, or even including lagged outcomes, or you can even think more broadly like synthetic control and related methods are doing something similar to basically saying, let's match exactly on lagged outcomes or lag trends, something like that. So similar types of issues apply there, where you can either be finding good controls or you can be selecting sort of a noise in the pre-treatment period. And then you can get additional bias from sort of this mean reversion type of effect. So there's some nice papers. My co-author on the review article, Alyssa Belinsky and Laura Hatfield, have a paper on regression to the mean in matching difference and differences. And then Sylvain Chabet-Ferret, excuse my horrible French, has a Journal of Econometrics paper kind of thinking about these types of issues. And so it's kind of in this slightly uncomfortable land where, depending on what the data generating process, conditioning on the lagged outcome can either help you a lot if you're getting like really good matches, but it can also help, sort of hurt you a lot if there aren't really any good matches, but you're just sort of conditioning on finding the matches that had the biggest noise in the pre-treatment period so that they look like good matches. So that's another area where I think kind of, unfortunately from the data, it's a little bit hard to tell whether this is helping you or hurting you. And so some sort of economic knowledge about, well, what's the right model of the world can be helpful there. Cool. Are there any other questions, Bacon? Great. So just to kind of summarize what we've talked about so far, what are limitations of pretrends testing? So the first limitation of pretrends testing is that pretrends tests may have low power. So what that means is we may not find a significant pretrend, even if parallel trends is violated, just because we have noise in our data. And so our confidence intervals may include zero, even if the true pretrends are not zero. The second issue we talked about was issues related to pretesting. right? So there's this selection bias if we only analyze the cases where we have an insignificant pretrend, and that in some cases can make things worse. And then there's a third issue, which I haven't talked about yet, but I think is pretty simple, which is that sometimes we find a significant pretrend, and then there's the question of what happens next, right? So we often still want to learn something about this, treatment of interest, both because we care about it and because we got to publish papers to get tenure and whatnot, right? And so the current approach says, look, if you find a significant pretrend, pre-parallel trends probably doesn't hold exactly in the post-treatment period because it didn't hold in the pre-treatment period exactly, but does it really mean that we can't learn anything? What can we do, especially if the pre-trend is significant, but it's small in magnitude? We might hope to actually still learn something about the treatment effect of interest. And so I guess you might ask, well, what can we do about these issues? And so I'm going to briefly try to talk about two different approaches to dealing with these issues from the two papers that I've kind of been basing this talk on. And so the first is kind of what I'll call a very low touch intervention, which is just to kind of think about diagnostics of how likely would we be to have good power in our pretrends test, and what would the likely distortions from pretesting be under some, sort of hypothesized economically relevant trends. So that'd be the first approach that I'll talk about, I think, relatively quickly because I have 20 minutes left. And then the second approach, which is sort of my preferred approach, will be the sort of formal sensitivity analysis that sort of avoids running the pretests exactly, but tries to sort of formalize a lot of the intuition that I think is motivating the pretesting to begin with, and has some of these nice features that I mentioned to Bacon, like your confidence intervals will get wider if your confidence intervals for the treatment effect will get wider if your confidence intervals for the pretrend are also wider. And I should mention that these are both available in R in the pretrends and honest DID package. And one of the things that I get asked most when I present this is there a Stata package? And the answer for now is unfortunately not, but I have some RAs this summer kind of working on at least starting out with an honest DID package, which I think should be ready to be released in a beta version in the next month or two. And so hopefully we'll soon at least have an honest DID Stata package, and then hopefully after that a pretrends package as well. So for now you can do these in R, and the pretrends package also has a Shiny app where you can upload estimates from Stata, and hopefully soon there'll be a more fully fledged Stata option as well.
Should also plug here, I've used the honest DID package in R to great effect once, but I am by no means an R user. And if anybody else is also like me, last summer EHEC had a really great sort of tutorial with Grant McDermott about using R. So there are resources out there to hopefully get you up to speed to use these R packages as they exist now, because I think they, at least for me in my own applied stuff, they've already really been helpful.
Awesome. So thanks, Bacon. So let me just jump in. I'll go quickly over kind of the pretesting diagnostics and then mainly talk about honest DID. But let me just show you kind of this pretty screenshot that took me many hours of coding to sort of get to. So I like to show it off of kind of what the pretrends package can do for you. So here I have in black, in the black bars, I have those original estimates from that He and Wong paper that I showed you at the beginning. And then what you can do with the pretrends package is you can hypothesize some difference in trends in the red here, see with these squares. And what I like about this package is it lets you kind of formalize a little bit what I do in my head when I'm in a seminar and someone puts up an event study plot, which is I sort of ask myself, can I draw a straight line through all of the confidence intervals of the event study coefficients, or maybe not a straight line, but some, very smooth line, and sort of explain all of the effects with, some sort of relative, seemingly reasonable pre-existing trend. So you can sort of do that with some hypothesis trend. You can put in anything you want here. It doesn't have to be linear. You can sort of see it on the plot. So that's what we have in red. That's sort of a user input. What might a hypothesized difference in trends look like? And then in blue, what I plot here is sort of, if the truth were this red line, what would I expect the coefficients to look like conditional on not finding a significant pretrend? And so you can sort of see from this plot that, all of the patterns that we see in this event plot, it seems like could be explained by some pre-existing, say, linear or smooth pre-trend. And I want to emphasize that if the plot looks like this, it doesn't necessarily mean that there's no treatment effect. It doesn't necessarily mean that the truth is this red line. We indeed can't rule out that there was a zero pre-trend, right? So we can't rule out that they were moving exactly in parallel. And if we had a lot of, ex ante knowledge that these two groups should be really similar, say they were basically randomly assigned, then this might be okay. But what this plot is sort of telling us is that it's very hard to distinguish from the data whether the truth is that there's no pre-trend or the truth is that the pre-existing trend is something that looks like this red line. And so in addition to these pretty plots that you can make, the package can also calculate some more formal statistics, like what is the power? So what is the likelihood we would find a significant pre-trend if the truth were that red line? And then we have some other related types of measures that in the interest of time, I think I'm not going to go into the details. So what I like about this approach is that it's very intuitive and it's easy to visualize. And I think it helps to identify cases where pretesting for pre-trends may be the least effective. So it helps to highlight the cases where, there's some pre-trend I'm worried about. I can see from this package, actually, I have horrible power to detect that. I'd only detect it like 10% of the time. And so I should be concerned, or I should at least be sanguine about the fact that I'm not going to learn a lot from the pre-trends test, whether it's this violation of parallel trends or it's actually zero. And then I think the thing that's also nice about it is that this approach requires relatively little change from standard practice. So you can estimate what you were planning to estimate anyway. And then you can sort of assess, well, would I be well powered to detect a violation of parallel trends in this example?
So in that picture, the plot that you just talked about, in like the worst case scenario, is it that I would have estimated pre-coefficients that were kind of trendy looking on their own. Then I've hypothesized a trend that fits those pretty well, and the confidence intervals are really big. So the expectation, given that I don't pass, is really not even that different from the line and the dots themselves, and just like everything looks bad. That would be like a bad outcome for this plot. Is that true?
I think that's right.
Okay, and then like using this method, what would be a version of making a plot like this that makes you say like, oh wow, this actually is working really well. This is great.
Yeah, so I guess the version I should maybe in the slides, I should have another version to say. I at one point, I think when I taught my undergrads, I had like my, like sort of when you go to the ophthalmologist and they have like A or B, and it's like this one looks good and this one looks bad type of example. So I don't have the B where it looks really good. But if you thought of like all of these coefficients were really tight around zero, and then like the post ones were really tight, like up here at 0.4, then like any type of smooth thing that you draw through all the intervals would come like nowhere close to the estimated post-treatment coefficients, right? So then you would sort of say, if the pre-trend were smooth, then, it could be there's a little bit of bias, but it would be very small relative to the magnitude of my estimated coefficients. And
okay, and then actually Amanda Creeder asks this in the chat, but I was going to ask too. I have been up till now like thinking about what you're talking about largely in terms of the pre-coefficients, and obviously you discussed their implication for like what we find in the post period. But can you just say one more time, like what's the interpretation of the blue triangles? And then I'm kind of adding this. Can you like emphasize to what their interpretation is in the post period as well? Yeah.
So let me start with the red squares, which are easier, right? So the red squares, this is just some hypothesized trends. Right, so that here the post red squares are just the extrapolation of these red squares in the pre-period, right? So if the true trend were linear and the pre-trend were these 3 red squares to the left, then the bias in the post would be these 4 red coefficients. Or in other words, if there were no treatment effect and this were the pre-trend, then these 4 red squares to the right would be the average of my estimated coefficients for the post.
But your hypothesized value in this exercise doesn't need to be a line. It's just a line in this picture. You could hypothesize an actual trend break, right?
Or exactly.
Okay.
Exactly. And then so then the blue is if the truth is the red. So on average, you would get the red over all draws of the data generating process. The blue is what would the average be conditional on not finding a significant pre-trend.
Okay, and so this is like combining real estimates with your simulation from before about how you would get kind of like a trend break looking thing just because of pre-testing plus noise.
Exactly.
Okay.
Cool, great. So I think I talked about the pros of this method. It's very easy, it's very intuitive. Kind of the cons of this method are in some ways, especially as an econometrician, it's not so theoretically satisfying. So one thing about that's not so satisfying is power is always going to be less than 1, right? So even if I say, it looks pretty good, I'm powered 90% against what I think is like a reasonable violation of parallel trends. Well, that means 10% of the time I'm not going to find it, right? And so the kind of unbiasedness of my coefficients and the validity of my confidence intervals depends on parallel trends holding exactly. And so 10% of the time, those aren't going to be valid. And so, based on this approach, even if I have good power, I'm still not getting some estimates and confidence intervals where I have, real statistical guarantees. Another issue here is that you need to specify some hypothesis trend, some red line in that plot. And sometimes it's going to be difficult with this approach to summarize over many possible, hypothesized trends. And then lastly, it's still not clear exactly what to do when we do reject the pretest. So if I find a significant pre-trend, then, I may still be, I may still want to say something, but, I don't really know from this approach what exactly I'm supposed to do. So that brings me to the second solution I've proposed, which I find to be kind of the more theoretically satisfying solution, which is in this paper, a more credible approach to parallel trends, which is associated with the honesty ID package. The idea behind this paper is that we think the intuition behind testing for pre-trends is that we have some prior that the pre-trends are informative about what the post-treatment difference in trends would have been in the counterfactual where the treatment hadn't occurred. Right, so what we really care about is what would the difference in trends have been after the treatment if there hadn't been any treatment. And we look at the pre-trends because we think if those are small, that probably that counterfactual difference in trends would have been small. If those are large, then we're more worried that those counterfactual differences in trends would have been large. And so basically this paper tries to formalize that intuition by imposing a variety of assumptions that sort of formalize this idea that the true counterfactual difference in trends can't be too different from the true pre-trend. And so with those types of restrictions, we can then bound the treatment effect of interest, and we can also obtain valid confidence intervals under the imposed restrictions that sort of account for the fact that we've only noisily estimated the true pre-treatment difference in trends. And so we think that this approach kind of enables a very natural sensitivity analysis where we can say sort of how different would the counterfactual trend have to be from the pre-trends in order to negate a particular conclusion, say a positive significant effect. Let me tell you about this in a sort of stylized 3-period model similar to the simulations that you saw earlier. All of this will extend to multiple period models, and I'll show you an application where we have multiple periods, but it's sort of easiest to first think about it in the toy 3-period model. So we're going to have 3 periods where the treatment occurs in the last period, so we can estimate 1 pre-treatment diff and diff, and then 1 post-treatment diff and diff. And so the thing that we actually care about is the bias of the post-treatment diff and diff, which we'll call delta 1. What is delta 1? It's the difference in the evolution of Y0, so the untreated outcomes for the treated group, minus the difference in the evolution of Y0 for the control group between period 0 and period 1. And unfortunately, we can't directly calculate delta 1 because we don't see what would have happened in the counterfactual for the treated group. But the nice thing is that, this nice feature of the diff and diff design is that we can estimate a analog to delta 1, which I'll call delta minus 1, which what is this? This is the diff and diff in the untreated potential outcomes, not between period 0 and 1, which is what we care about, but between period -1 and 0, right? So we can estimate this pre-treatment trend in these untreated potential outcomes. And so the key idea here is going to be, if you told me the true, I had data for the full population, you told me the true delta -1, this pre-treatment difference in trends in the population, then I think that tells me something about the possible values of delta 1, right? And that makes a lot of sense because the reason I'm testing is the null hypothesis is delta -1 equal to 0. is because I think if delta minus 1 is close to 0, that delta 1 is likely also close to 0. Right? And so the key idea here is we're going to place some restrictions on what are the possible values of delta 1, the counterfactual post-treatment difference in trends, given the value of delta minus 1, the pre-treatment difference in trends. Right? So intuitively, these types of restrictions are going to say that the post-treatment difference in trends delta 1 can't be too large relative or too different relative to the pre-treatment difference in trends delta minus 1. So you might ask, well, what types of restrictions might you place on the relationship between delta 1 and delta minus 1? So one restriction that we consider bounds sort of the relative magnitudes of these two differences in trends. So one requirement would say that delta 1 is less than or equal to an absolute value than m bar times delta minus 1. So I set m bar equal to 1, for instance, that I'm saying that parallel trends can be violated in the post-treatment period, but by no more than the magnitude of the violation in parallel trends in the pre-treatment period. So if I thought, there may be differential economic shocks to these different groups, but they're about the same in magnitude in the pre-treatment period as they are in the post-treatment period, then m bar equals 1 would be reasonable here. If I thought maybe in the post-treatment period, was a more turbulent time, they could be up to twice as large, then I might set m bar equal to 2 here. So that's one type of restriction that we consider. A second type of restriction that we consider is what we'll call a smoothness restriction. And so this kind of builds on the common practice of sort of controlling for a parametric group-specific linear trend. So if we thought there actually were a parametric group-specific linear trend, if you told me delta minus 1, I could take this line, I could continue it to the post-treatment period, and I would get that delta minus 1 is exactly that delta 1, this counterfactual post-treatment difference is exactly minus delta minus 1, right? So it's exactly what I would get if I just continued this black line. But often we think things kind of are evolving smoothly over time, but they might not be exactly linear. And so we can think about relaxations of that assumption behind the common practice of controlling sort of parametrically with a linear trend to allow this linear trend to be approximately right, but not exactly right. So we can think about a smoothness restriction where we say if we do this linear extrapolation between consecutive periods, we might not be exactly right, but we're not going to be off by more than this factor that we call m. And so you may ask, well, when should I do one of these versus the other? In the paper, we sort of have two different applications, one of which where we think the bounds on the relative magnitudes is more natural, and one where we think the smoothness restriction is more natural. So I'm going to show you the first one, but just to kind of give you an overview of the two and when you might prefer one versus the other. In the case where we use relative magnitudes, we sort of are worried about different macroeconomic or industry level shocks because we're comparing two different sets of industries that may sort of get different shocks in different periods. And so we don't think that those shocks are necessarily following a smooth trend, but we might think that the magnitudes of those shocks in the post-treatment period are not too different from the magnitudes of those shocks in the pre-treatment period. And so something like bounds on relative magnitudes, we think makes a lot of sense. In the second case, we're looking at sort of female labor supply in different states, and we're thinking about long-run trends in female labor supply. And so there we're worried about things like, women entering the labor force is happening faster in, say, Democratic-leaning states than Republican-leaning states. And so that's a case where, even in the original papers, they were thinking about robustness to linear parametric trends. And so thinking about kind of relaxations of that type of extrapolation make a lot more sense. So one thing that we think that's nice about this approach is you can sort of use economic knowledge about what violations of parallel trends might look like to kind of inform what restrictions you put on how these delta 1s relate to the delta minus 1s.
Okay, can I ask another question about sort of implementing this? So
Yeah.
like when I went about doing this, I faced this choice about like which of these kinds of parallel trends violations am I going to allow? And one thing that I was kind of finding when I was getting used to the command and getting used to what this method produces and how to use it is, like when I was pegging my parallel trends violations to the biggest estimated violation in the pre-period, that was sometimes kind of sensitive to noise. And I don't mean noise like confidence intervals. I mean like if my pre-period was flat and pretty good, but it was kind of the point estimates were bouncing around, the command would take like the worst period to period variation.
Yeah.
And it would look really, 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 really bad. But I mean, if you looked at the whole pre-period, that's not like the way that the dots were looking on average, really. So how should I think about, I mean, I think I like your explanations based on like which kind of context you're in. Like, is it a long run smoothness kind of evolution thing, or is it something else? But how should I think about the difference in the meaning of reporting out results from honesty idea based on like a relative magnitude versus a smoothness restriction, like how to choose them and how to discuss them?
Yeah, so I think you make a great point, which is actually it brings me nicely to my next slide, which is here we're talking about restrictions on delta 1 and delta -1, which are basically saying, if I told you the true delta -1, the true pre-treatment difference in trends, then I would say that the true post-treatment, counterfactual difference in trends delta 1 would be less than or equal to m bar times delta -1, right? So this is a restriction on basically the population differences in trends. Obviously, in practice, we don't actually see delta 1 and delta -1. We see basically an estimate of delta -1. We'll call that beta hat -1. That's our pre-trend coefficient. And then we see our post-treatment coefficient, which is the sum, or an estimate of the sum of delta 1 and the treatment effect, right? And so I think what you're talking about, Bacon, is basically we're going to have a method that's going to account for the sampling variation, that like we don't see delta -1, we only see this beta hat -1. And so if that beta hat -1 is very noisy, then it could be that, we can't rule out that in some pre-treatment period, there was like a big difference in trends. And so that sort of leads to, your confidence intervals for the treatment effect are going to be wider if your pre-treatment coefficients are noisy, which I think in general is a feature rather than a bug, right? Because if we're unsure what the pre-trend is, then we kind of unsure about what the bias is if we think, the bias in the post is related to the bias in the pre. But to your particular question, sort of if you're bounding, you're saying the post-treatment bias is no worse than the max pre-treatment bias between consecutive periods, then if you have any noisy estimate in the pre-period, then sort of that's going to be very big, right? Because we can't rule out that between period -9 and period -8, the trend was really big. And so if we're ruling out relative to that, then our upper bound on how big that difference in trends is could be really big. There is one thing that you can do, which is like, if you're willing to restrict that basically the total violation of parallel trends over 2 post-treatment periods is no larger than the total violation of parallel trends over any 2 consecutive pre-treatment periods, which I think is sort of the intuition that you had, that you were saying, which is that, they may bounce up and down in the pre-treatment period, but kind of if you average them over multiple periods, they seem pretty close to 0. So one thing you can do is like, if you're willing to make that type of restriction, you can sort of run honesty ID after you've sort of binned the pre and the post. So you could sort of, pool your coefficients so that each of those corresponds with like a 2-year interval or something like that.
I see.
And then run it. And so then you'll sort of be bounding the violation across any 2 post-treatment periods relative to the sort of the max or the upper bound of the confidence interval for the max over any 2 pre-treatment periods.
Yeah, I see. And sometimes people will do that for precision reasons anyway. So you might be washing out noise in terms of what's the magnitude you're going to peg to, and helping in terms of the size of the confidence interval that's getting fed into the command. Is that right?
Yeah.
Okay.
Cool. So great question. So I know I'm at time, but if we can, people should feel free to leave whenever they need to leave. I guess I'm not sure I have to say that on Zoom, but if we have another 5 minutes, I'd love to show you sort of how we can use this in an application.
I think that'd be good. And I think our hard stop is 2:45. So we have like 13 minutes before like the whole thing shuts down.
Okay, great. So I don't think I will need 13 minutes.
Yeah.
But I'll take 5 and then happy to take any questions. And then I'll be in I don't remember what it's called, but whatever the virtual environment that we're using afterwards is, if people have additional questions. One of the applications that we have in the paper is to this paper by Benzardi and Carloni, where they're looking at what happens if you cut the value-added tax on restaurants. So they're using this policy change in France in 2009 that sort of dropped the VAT on restaurants from about 20% to about 6%, but didn't change the VAT for firms in other industries. And so they're using fairly vanilla, non-staggered differences, comparing restaurants to other firms. And one of their key outcomes here is going to be profits. So a big finding of this paper is that profits go up a lot for restaurants surrounding this reform. So a lot of the incidence of this tax cut is going to restaurant owners rather than, say, restaurant consumers. And so here you can see the event study plot for log profits, which is one of the key outcomes in this paper. And it turns out actually they do have a significant pre-trend. So this coefficient for 2007 is quite significant. And in fact, these 4 pre-treatment coefficients are actually jointly significant. But if you kind of just eyeball this plot, it does look like there seems to be a much larger change post this treatment than there was, kind of in any of the, consecutive pre-treatment periods. And so what we're going to do here is we do a sensitivity analysis where we're going to compute our robust confidence sets under the restriction that the counterfactual difference in trends between 2008 and 2009, so this first year after the reform, is no larger than some multiple times the largest true pre-treatment difference in trends in the pre-period. And we think this makes sense because here we're worried about, are there differential, macroeconomic factors, say, that affect, restaurants differently from, other market services firms. And so we don't necessarily think that those shocks would be monotone or following a smooth trend, but we might be willing to benchmark the post-treatment magnitudes of those shocks relative to the pre-treatment magnitudes of those shocks. And so what I have here is a sensitivity analysis plot where in blue, I have the original confidence intervals from OLS if we assume parallel trends holds exactly. In red, I have robust confidence intervals where I'm allowing for that post-treatment violation of parallel trends in the population to be positive, but to be no more than M bar times the largest violation of parallel trends in the pre-treatment period. So I set M bar equal to 1, I'm saying the difference in trends between 2008 and 2009 in the counterfactual where treatment hadn't occurred could be no larger than the largest true difference in trends in the pre-treatment period. And so you can see that, for instance, if I set M bar equals 1, so I say these post-treatment counterfactual differences in trends can be no larger than the max in the pre-treatment period, I get this confidence interval, which is wider than the OLS confidence intervals where I say parallel trends holds exactly, but I can still rule out a effect on profit smaller than something like 7.5%. So I can still rule out that there was a zero pass through to restaurant owners from this change in the tax reform. Of course, if I allow for the counterfactual difference in trends in the post-treatment period to be much larger than the largest thing I saw in the pre-period, then my confidence intervals are going to get wider, and sort of the lower bound of the confidence interval crosses 0 at right around 2. So this basically says that I can rule out a 0 effect on profits unless I'm willing to allow for the post-treatment difference in trends to be twice as large as the worst difference in trends in the pre-treatment period. And I should point out that the confidence intervals here are taking into account the sampling uncertainty in the pre-treatment period. So we have some estimates of pre-treatment differences in trends, but these confidence intervals are sort of taken into effect that they're confidence intervals around what that true pre-treatment difference in trends is.
Okay, so I often estimate these things, and then I fiddle with my point estimates in the paper to say, like, is this a plausible magnitude, or how does this compare to another paper, or how does this estimate compare to this estimate? So there's like a lot of little back of the envelopes, that come in the last third of my papers. How should I be thinking about talking about reporting magnitudes when I've done a sensitivity analysis, and say I actually do probably think that a violation with M bar equal to 1, that's just, so like I do think that the post-treatment violations are maybe about as bad as the worst pre-one. What if I think that's true? Now I've got a confidence interval, and I could say, well, in this paper, it's not that there's no effect, but I've got this big range. Like, what do you think would be a responsible way to discuss that?
Yeah, great question. So I guess the first thing I would say is I think, we're used to dealing with confidence intervals, right? And so in some ways, we already have ways of dealing with these things, which is like we say something like, the consensus estimate from the literature appears to be around 0.3. The lower bound of our confidence interval is actually, 0.35. So we can sort of rule out the consensus estimate from the literature, but maybe our confidence intervals overlap with some of the individual estimates in the literature. So now here you have a confidence interval that has a particular robustness property to it, but I think you can sort of deal with it in a similar type of way as you would a normal confidence interval, assuming, as you said in your example, that you sort of believe M bar equals 1 is reasonable. I guess there's a question of, sometimes, is M bar equals 1 reasonable? Is 1.5 reasonable? Right. So then you sort of get into those, well, like, which one do I go with? One kind of nice thing that I like here, which I reported here, is what we call kind of the breakdown value of M bar. Right. So here I reported the breakdown value for a null effect, which is basically like, how big would I have to allow these differences in trends to be in the post period relative to the pre-period in order for me not to reject the null hypothesis? In this case, it was of 0. But if the consensus elasticity in the literature was 0.3, you could sort of report, well, what is the breakdown value of M bar in order for me to reject the consensus from the literature, or something like that. Does that help?
Yeah, I think so.
Awesome. So we have 5 more minutes until our full stop, our hard stop. This is basically what I wanted to show you guys today. So why don't I stop here, and then happy to take any questions in the 5 minutes that we have left.
So anybody else can can put in the chat, and we can relay. If we're waiting for anything to come in, I mean, I don't know how to make Ezra's computer completely just kick us off before he's got to go somewhere else. So let's make sure that we wrap up and move over to Kumo space. Shushan put the link into the chat, so people should jump over there and move your little Kumo space avatar around and listen to more about different diff stuff. But yeah, why don't we, unless anything shows up at the moment, why don't we leave it there? Thanks so much, John. This stuff is really interesting, and I always think of it as like this other level on top of the new diff and diff stuff. Like it applies to everything. I know there's one question in the chat about like, does this apply to the new things? And I kind of answered for you and said, yes, all of this applies. Doesn't matter what new estimator you use. Like it's all just a general diff and diff kind of set of lessons.
Oh yeah, crap. So I skipped my summary side. I guess this is payback I get for putting new material into the summary side at the end. But I did want to flag that, as Bacon mentioned, these tools sort of play nicely with recent estimators developed for heterogeneous treatment effects. Also with estimators for conditional parallel trends and stuff like that. So Pedro Santana has a nice sort of example on his website of how you can use this with the DID package that does Callaway and Santana. And we're actually working on kind of a more formal integration between our two R packages for that. I guess once we produce our Stata package, we can also try and do integration between the Stata packages. But kind of, I think one nice thing about our honest DID approach is basically is sort of, a function that takes in results of any event study plot. And so as long as you have some way of generating an event study plot where you have some betas and you have some standard errors for those things, you can sort of feed that in to the honest DID. And so it sort of plays very nicely with a lot of different types of things that people want to do.
Yes, that's good for the 101 people still hanging around. This is not something I understood at first. I thought my using of the honest DID package, I thought I was going to be uploading my data and re-estimating things, which for some reasons that are my problem, I did kind of do that, but you don't have to do that. You just get your output from whatever you need, and you just give these packages point estimates and confidence intervals or standard errors. And that's everything. Everything John talked about is that there's like there's like no microdata in what you talked about today, just estimates, right?
John,
I guess the slightly tricky thing is you need a variance covariance matrix, not just the standard errors. But
yeah, right,
you can get it's the E of V in Stata, so it's not too bad.
I don't know if this is the typical response this level of quietness is the typical response you get in a seminar, but I don't know how others are feeling, but I definitely feel like everything I know is a lie, and I need to go back to every event study I've ever estimated and think about it again. So it really, the figure you showed about how the pretest bias and how simply, just based on the abnormal draw you get from the data, you could end up with a hockey, that hockey stick shaped figure that we all love to see. That was very chilling. So there will be a lot of people, I'm sure, who will be going back to this this recording and don't take the health economists being very quiet as our lack of interest. We're all probably mulling all of the sins that we've committed in the past. This is really fantastic. And thank you so much for coming.
Oh, well, thank you. And I hope not to create any nightmares for people. So, I wrote the problems with pretesting paper first, and then, I don't just want to ruin people's, hopes and dreams. So I also tried to come up with honest deity afterwards to try and help with some of these things. So hopefully, I feel bad for increasing the lengths of people's appendices in their papers and stuff, but I'm hoping that,
and right, the whole point is to seek the truth, right? So we all want to find the truth. So all these tools are great. And just having someone decode them is fantastic. Anyway, all right, so I guess we'll all leave and go over to Kumo space if you like. Thank you so much for coming, and thank you, Jonathan, so much.
Yeah, thanks so much for having me. And I'll see you guys in the Kumo in just a minute.
Okay.